This video is designed to explain why we need to use available potential energy, or APE, to understand the ocean circulation. We're going to start by explaining why regular gravitational potential energy is actually not a good descriptor of ocean energetics. Gravitational potential energy, written here as GPE, is defined as the integral of density ρ times the acceleration due to gravity g times the height z integrated over the volume of fluid v. Now, there are three reasons why GPE is inappropriate for the ocean. The most obvious is that GPE is arbitrary, in that it depends on the definition of the origin. So to demonstrate this, we're going to use the example of a rectangular box of fluid with surface area A, height h going from ZB at the bottom to ZS at the surface, and constant density ρ0. Now, since the density is constant, the GPE of this box of fluid is simply the integral from ZB to ZS of ρ0 g a z dz, from which we extract the constants to give ρ0 g a on 2 times the difference between z squared at the surface and the bottom. Here we see that if the origin is defined to give z equals 0 at the bottom of the tank, then GPE is simply ρ0 g a z squared on 2. On the other hand, if we define the origin at the surface, as is commonly done in ocean models, then GPE is the negative of the same quantity. In other words, the sign and the magnitude of GPE is determined entirely by where you define the origin. Now, the arbitrary nature of GPE is well known, but the common counter-argument to this problem is that we should concern ourselves with the change in GPE rather than its absolute value. But the second reason why GPE is not useful for the ocean is that the change in GPE can also be an arbitrary quantity. To understand how this can occur, let's consider the GPE evolution for our simple rectangular domain, where we now allow density to vary in both space and time. The GPE evolution equation is therefore the time rate of change of GPE on the left is equal to g times the integral over volume of d rho dt times z dv. We can evaluate the right-hand side of this equation by assuming that density is governed by a straightforward advection diffusion equation, or d rho dt plus u dot grad rho equals kappa grad squared rho, where u is the velocity vector and kappa is the diffusivity. Equivalently, we can write this in flux form. D rho dt equals negative times the divergence of rho u plus kappa grad squared rho. We also need some boundary conditions on this domain, and we'll assume that the flow in our rectangular domain is subject to no flow through all boundaries, in other words, u dot n equals 0 on the boundaries, and that at the upper surface there is a buoyancy flux, F, which we write as k times d rho dz, while all other boundaries are insulating grad rho dot n equals 0. So we're now in a position where we can substitute for d rho dt in the GPE evolution equation, giving d dt of GPE equals g times the integral over area of the integral from zb to zs of negative z times the divergence of rho u plus z times kappa grad squared rho. Obviously, the lateral advective and diffusive terms integrate to 0 on the side walls due to Gauss's law and the no-flux boundary conditions, leaving just the vertical term. These can be handled by integration by parts to give g times the area integral of negative rho wz plus kappa z d rho dz evaluated between zs and zb, plus the integral between zb and zs of rho w minus kappa rho z dz. Now, of the four terms on the right-hand side here, the first is 0 because w is 0 in both boundaries, while the second term becomes simply zs times the surface boundary flux integrated over the surface area. The third term is the interior buoyancy flux, rho w, while the final term integrates to give the net vertical diffusive flux of density, which, being a linear operation, is just proportional to the difference between the top to bottom mean density. So the last term on the right-hand side here is a positive definite source of GPE in a stably stratified fluid, and it's essentially a conversion of internal energy to GPE. The second term here is the bidirectional conversion between potential and kinetic energy, and both of these terms are indeed independent of the definition of the origin. However, the first term, which is the input of GPE from surface buoyancy flux, is only independent of the origin in the special case of horizontal convection, in which net buoyancy flux is constrained to be zero. Thus, we argue that in the presence of surface buoyancy fluxes, the rate of change of GPE is also an arbitrary quantity. This special case of horizontal convection, where the net surface flux is zero, highlights the third and most significant problem with using GPE, namely that it obscures the dynamics which arises due to surface buoyancy fluxes. This case was most famously highlighted by Paparella and Young in their 2002 paper, but others have pointed out that GPE is not altered by surface buoyancy flux if F is balanced. However, this result is at odds with experiments and numerical simulations in which a finite circulation can be maintained at equilibrium in the absence of mechanical forcing. We're going to demonstrate this issue with a simple example. Consider a box of fluid with the lower right corner removed, as I've shown here. Initially, we're going to assume that the fluid in this box has a constant density ρ0, and we'll call this case 1. We can calculate the GPE of this fluid to be simply ρ0 g A on 2 times h squared minus little h squared on 2. This calculation is done assuming that the origin is at the base of the tank. Then I'm going to compare this with a second case, case 2, in which the upper right-hand half of the fluid is made denser by a small fraction, delta rho, and the upper fluid on the left-hand side is decreased in density by the same amount. Intriguingly, this rearrangement of density doesn't alter the total GPE, meaning that GPE2 is the same as GPE1. Yet we know from experience that case 1 and case 2 will behave very differently. Just to labour the point here, we've done some simple lab experiments with these two cases. In the upper panel here, you can see case 1, where we've dyed the water on the shelf to track fluid motion. However, any motion in this part of the tank simply results from the disturbance generated by removing the barrier, because there are no density differences to drive a net flow. On the other hand, when we remove the barrier from case 2, we get a strong and sustained buoyancy-driven flow which creates secondary turbulence and mixing. The forcing needed to go between the initial states for case 1 and case 2 is similar to the zero net surface buoyancy flux in the horizontal convection case. Hence, there is no input to GPE from this transformation. We argue that these two cases can only be understood if one measures potential energy relative to a reference state. The usual reference state for a stratified fluid is that proposed by Winters et al. 1995, which is that we create a hypothetical background state in which all densities are resorted adiabatically into a statically stable density profile, akin to running the case 2 experiment with immiscible fluid. The resulting reference state for case 2 has the densest fluid, ρ0 plus delta rho, at the bottom of the tank, and the lightest fluid, ρ0 minus delta rho, layered across the top. With some calculation, we can also write the potential energy of this hypothetical state, the background PE or BPE, as BPE equals GA on 2 times ρ0 h squared minus little h squared minus delta rho on 4 h squared minus 2hh plus 3 little h squared, which is just slightly less than the original GPE. On the other hand, BPE for case 1 is exactly the same as the GPE. The measure of potential energy that we are advocating is the available potential energy, or APE, defined as the difference between GPE and BPE, which in case 2 becomes G times A times delta rho on 8 times by h squared minus 2 little hh plus 3 little h squared. APE is all the energy that could possibly be converted to kinetic energy. Note that the reference state defined here is hypothetical. It is unlikely to ever be reached in a real experiment, and it may be possible to define other relevant reference states. To find the reference state more generally, we follow Winters et al. In 1995 to define a new quantity Z star. Now Z star is the height that a parcel of fluid would take in the reference state, and can be written most elegantly as Z star as a function of space and time as 1 on A times the integral over the volume of the Heaviside function of rho of x prime, comma t, minus rho of x, comma t, integrated over the volume. Z star is therefore a 3D function which can be used to calculate the background potential energy. That is, BPE simply equals the integral over volume of rho times g times Z star dV. We can then write APE as the integral over the volume of rho times g times Z minus Z star dV. The advantages of using APE as our measure of potential energy in the ocean are firstly that it is independent of the origin. Secondly, that it captures the only part of GPE that can be converted into kinetic energy, that is, the dynamically useful part of GPE. And thirdly, we show below that it can account for the effect of surface buoyancy fluxes on ocean energetics. To make the calculation of energetics including surface buoyancy fluxes, we follow the procedure we used to calculate the evolution of GPE and write the rate of change of BPE equals G times the integral over the volume of negative Z star times ddz of rho W plus kappa Z star times rho ZZ dV. Winters et al. 1995 have previously showed that the advective term in this equation cancels, but the derivation is a little convoluted, so we won't reproduce it here. Instead, we're going to focus on the second term, which we integrate by parts to give G kappa times the integral over the area of, firstly, the difference between Z star d rho dz at the surface and the bottom, plus the integral from ZB to Z star of dz star dz times d rho dz dz dA. Now the first term is once again connected to the surface buoyancy flux, and it can be simply written as G times the area integral of Z star at the surface times F dA. And the second term can be rewritten as G times kappa times the integral of dz star d rho times d rho dz squared integrated over the volume. The latter term here is positive definite, and it's the rate at which energy is lost from APE to BPE by irreversible mixing, as discussed extensively in Winters et al. 95. The first term is discussed in detail by Hughes et al. In 2009. It represents the creation of APE from surface buoyancy fluxes. This term is actually saying that if surface buoyancy fluxes act to make dense water more dense, then BPE is converted to APE. Once it's available, this energy can then be converted to kinetic energy. That is, it possesses the energy to drive an overturning circulation. However, this source of energy is omitted if we only consider the evolution of GPE. We can explicitly write an APE evolution equation to show this, because the time rate of change of APE is simply equal to the time rate of change of GPE minus the time rate of change of BPE. In other words, we can write it as G times the area integral of Z at the surface minus Z star at the surface times F dA plus G times the integral of rho W dV minus G kappa times the vertical density difference minus the irreversible mixing term G kappa dz star d rho dz squared integrated over the volume. To summarise this argument, it's easiest to write out an energy budget diagram. If we consider GPE in isolation, we can resolve exchanges with kinetic energy, noting that kinetic energy may also have mechanical sources and sinks, which we haven't discussed today. We also have two inputs of energy, that due to surface buoyancy forces, which is negligible when F is balanced, and the diffusion of the background potential density gradient, pointed out by Paparella and Young in 2002 as being small. However, we're arguing that the primary influence of surface buoyancy fluxes are omitted from this framework, and they only become apparent when the distinction is made between available and background potential energy. Remember, it is only APE that can be converted to KE, so terms that can produce APE can effectively control the circulation in a stratified fluid. Surface buoyancy fluxes can indeed produce APE from BPE through densification of already dense water. In an equilibrium motion, this effect is balanced by the rate at which APE is lost to irreversible mixing. The diagram shown here applies for a simple rectangular box, and there are many additional complexities to face when applying these ideas to the ocean. In particular, one needs to consider the complicated bathymetry of the ocean, the nonlinear equation of state which can create or destroy APE within the ocean interior, and the non-local nature of density resorting required to calculate the reference state. That is, whether a density change in one ocean basin should be able to remotely affect the energy reservoir in other basins. Nonetheless, we argue that the insight into the nature of surface buoyancy forcing and irreversible mixing provided by the APE framework is essential to understanding current and future ocean circulation.